So hello everyone. I wonder if this is going through. This is Upmanu Lal at Columbia University welcoming you to the webinar today. This is part of our series on America's water. Uh, we have a NSF-sponsored project where we are looking at water, energy, food, and climate sustainability in the U.S., particularly with a direction towards understanding the economic value of water across the country. As part of that series, we've had this series of webinars, and we've had about a dozen speakers so far who are all trying to inform us on different aspects of the issues. So it's my pleasure today to welcome Dr. James Shortle from Penn State University. I hope I said the last name properly. He's a distinguished professor of agricultural and environmental economics, a very distinguished career. The highlights, to some extent, I suppose, would be in water quality trading innovations. And he's talking today about policy innovations to address non-point source pollution or nutrient pollution from agriculture, which is one of the major challenges that we face not just in the United States but elsewhere. So with that, let me welcome Professor Shortle and open this up.
Thank you very much for that introduction, and thank you all who have joined for this webinar. And I do know some of you, so to those who I know, hello. So I'm going to talk today about what I call innovating public policy for addressing nutrient pollution from agriculture. I have lost my screen for reasons that I don't know about. And because it was there. Oh, now it's back. I'm good. Okay, good. So this is a topic that I have worked on for a very long time, and I think it's one that clearly is of great importance to water quality in the U.S. and elsewhere. I just want to comment very briefly, a little bit of context. So I live in the Chesapeake Bay watershed and have done work in the Chesapeake Bay watershed for a long time, and I've done work on agricultural pollution control for a very long time, and I have to say it's been over 30 years, and in that 30 years, not a whole lot has happened, and I've been talking about policy in this area for a very long time, but in the Chesapeake Bay watershed, because of the Chesapeake Bay total maximum daily load, we find that states in the watershed are really having to contend with this problem of how you address agriculture. So some of the things I'm talking about today aren't going to be just things I think generally we ought to do, but I think when we're in places like the Chesapeake Bay watershed and probably not too far in the future in the Ohio Basin, we will see states needing to do things to innovate their public policies. So I think there is significance to this today. So just generally, some things that you probably all know, but agriculture is a leading source of water quality problems in the U.S. and around the world. And there are a variety of types, but I think we're especially concerned about nutrient pollution, so eutrophication of places like the Chesapeake Bay, the dead zone in the Gulf of Mexico, and others. And when you look around the world, you do find numerous places where ecosystems are threatened by nutrient pollution. And there's this map that many of you may have seen that was from Diaz and Selman showing places where we have hypoxic and eutrophic areas. These show mainly, so they're showing coastal areas. You see a lot on the east coast of the U.S. And what happens in a lot of these places, you're bringing nutrients down rivers and they're causing problems in estuaries. But we also get a lot of atmospheric deposition that is also happening in these areas too, so that's a significant thing. This shows coastal problems, but we also have a lot of freshwater problems in this area as well. And in the news in recent years, we've had the problems in Lake Erie, which are not just a threat to ecosystems, but are just a threat to human health as well. This table graph shows the number of impairments of waters in the U.S. from various sources, and you'll see here that nutrients rank second in the number of impairments, followed by metals and some other things, but clearly that's an indication that nutrients are really important to us. And this is just another kind of look at the kinds of impairments. I think when you look at, oftentimes when we look at impairments of waters or water quality risks, people tend to look at human health risks. And we've done a really good job of addressing human health risks through keeping stuff out of water and by water treatment. But what we have a lot of problems with still are threats to ecosystems. So this table shows the types of impairments that we see, and you'll see most of them are related to ecological functions of water. So fish, shellfish, wildlife protection, a high number of impairments, in this case the percentages related to those, aquatic life and harvesting, a high number of percentages related to those, and we see that public water supply is kind of on the lower end of these. And then looking at sources, I'm going to talk about agriculture today, but we see ag and atmospheric deposition in many of these are of large importance. I think one thing we've learned a lot about in recent years is how important atmospheric deposition is, and partly it's hard to measure, but we're learning a lot more. But when we're thinking about atmospheric deposition, part of that's from burning fossil fuels, but it's also from ammonia emissions and from denitrification of soils in agriculture. So part of that atmospheric deposition part is actually agriculturally sourced as well. So this is a table on the impairments by states. Okay, I live in Pennsylvania, and you'll see why, if you're a person in Pennsylvania, water quality is really an interesting issue. We have the second largest number of stream miles in the U.S., with Alaska being first, and you see that by a long stretch, we have a huge number of water quality impairments by comparison to other states. So Pennsylvania is the leading cause of nitrogen going into Chesapeake Bay. It's about 50% of the fresh water going into the bay, significant source of phosphorus also. And when you think about pollution issues, water pollution issues in Pennsylvania, oftentimes people are thinking about Pennsylvania's impacts on the Chesapeake Bay, but this particular table shows just impairments within the state, and a very high number. Not all of those are agricultural, but most of them are. The other big one we have is acid mine drainage. So just turning to sort of what we need to do about this. So clearly what we need to do in terms of the types of actions, we need to be reducing the nutrient loads that come from agriculture. We need to protect, restore wetland streambacks, riparian zones. And to do these things, we really do need to have new policies for agricultural externalities. And oftentimes when people talk about how to address problems of the Chesapeake Bay or other ones, the problem will be cast in technological terms. We need to get BMPs on the ground. We need to do various types of measures. And I think what often is missing is the recognition that pollution control is, yes, a technological problem, but it's fundamentally a policy problem. We really do know the technologies that we don't know everything about them, but we do know the kinds of technologies that will keep nutrients out of water. The problem is that we have not had the policies that will actually get this done. And going back to what I was commenting on a few minutes ago in the context of the Chesapeake Bay and the states in the Chesapeake Bay watershed now being at the front line of this problem, what these states are discovering to varying degree is that the policies, they know the technologies, they've had to develop watershed implementation plans to protect the bay, but what they don't have are the policies that will get those in place. And what you see them struggling with now is how to get farmers and others to do what they need to do to get the practices on the ground. And that's where it's a policy problem, and that's what my interest is in the policies to do that. So when you look at what we do now, current approaches, and we've been doing this approach really since the Clean Water Act of 1972, except for large confined animal feeding operations, which are called CAFOs, there really is very little regulation of nutrients from agriculture in the U.S. So under the Clean Water Act, the federal government required technology-based effluent standards for point sources and created the NPDES system to require them, but it had the states take over control of non-point sources, and the states generally have, when dealing with agriculture, have relied on voluntary compliance strategies that rely partly on moral suasion. So moral suasion means persuading people that they need to undertake pollution control practices, so through education and other mechanisms, and then providing them with financial and technical assistance for BMP adoption. And so the USDA has provided a lot of resources through and our Natural Resource Conservation Service programs, the biggest one being the EQIP program, to get BMPs on the ground. And so we have been spending a lot of money on addressing the problem and practice implementation, but we find that we're not making the progress that we need to make. And so we are taking action, but we're not really having the kinds of results we want to have. This is evident in water quality assessments when we find that agriculture is a leading cause of our water quality problems. But there was this one conducted by the Natural Resource Conservation Service called the Conservation Effectiveness Assessment Program, which looked at conservation programs in the U.S. that put BMPs on the ground in agricultural watersheds. And we find that they have positive impacts, but they aren't achieving what we need to achieve in order to achieve our water quality goals. So we're really at a stage, and we have been for a while, where we have to ask, what is the pathway forward? Should we do more of what we've done in the past, which would be the voluntary compliance strategies, or do we need to do something new? And I'm going to argue that we need to do new things. So when you look at a voluntary compliance strategy, the people who adopt practices really adopt them partly for public benefits, but really primarily to serve their own objectives. So farmers do participate in conservation programs, that often the resources in these programs are oversubscribed, but we're not achieving what we need to do. And that's because if you think about this, you're not putting practices in the places where they will have the biggest impacts, and you may not be putting the practices that will have the biggest impact in those places. So really it's, I'm calling it anything, anywhere approach, because really it's sort of like it's not a random process, but it's kind of like throwing darts in the dark to address the water quality problem, and you may not be putting things where you need to have them. So our limited resources really aren't directed to the places and to the practices where they'll have the largest impact. And just as a little bit of evidence on this, this table shows you the cost per unit of various kinds of best management practices which states in the Chesapeake Bay watershed are utilizing as part of their watershed implementation plans for the Chesapeake Bay total maximum daily load. And you'll see a range of them there. So up at the top are some animal ones for reducing ammonia emissions. Then we have some that are feeding related one, precision feeding, poultry phytase. and we have some that are runoff plans, conservation plans, and so a whole suite of different kinds of practices here. And you'll see down there at near the bottom, stream access control with fencing, a really expensive type of practice, by far the most expensive practice per unit of those that we have here. And you'll see quite a bit of variation. Some of these we have at a cost of zero, and that's because they're actually beneficial to farmers. And they may actually have negative costs. We have just zero costs here, but some of them, though, are really expensive. So that's sort of the cost of them. And then when you look at their effectiveness on these two diagrams for nitrogen, phosphorus, and sediment, you'll see a lot of variation there. So again, I'm going to focus on the stream access control with fencing. This is a very popular practice. We do a lot of it in Pennsylvania. In the Pennsylvania's Watershed Implementation Plan, it is one of our most prominent practices for achieving the Chesapeake Bay TMDL for Pennsylvania, but it is one of the least cost-effective in terms of keeping nutrients out of the Chesapeake Bay. So there's kind of two things to take away from this. One is that practices vary a lot in their cost effectiveness, and here we're looking at their efficiency. The previous one, we were looking at their cost, and together they determine the cost effectiveness of them. A lot of variation in practices. Some are really, really cheap. Some are very expensive when you look at what they get done. And so this tells you that when you're thinking about doing the most with your limited resources, you really do want to look at the relative cost effectiveness of different practices so that you do get the biggest bang for the buck when you do that. Now, I want to have one little qualification on that. These numbers are for the purposes of protecting the Chesapeake Bay, reducing delivery of nitrogen, phosphorus, and sediment to the bay. When you evaluate some of these practices, though, for a local watershed, you might have a different view of the cost and effectiveness. So stream access control has nice impacts on local habitat. And so when you're thinking about the local benefits, it might be higher than what you would have for the Chesapeake Bay. And so you do have some issues of complementarities or substitutions in practices for serving local goals versus bay goals. So important concept there is this one of cost effectiveness. Another important one is the notion that places in watersheds deliver different amounts of nutrients, and in particular, we're understanding, and probably many of you as scientists know this much better than I, who's as an economist doesn't really study this particular thing, but we're learning that particular parts of watersheds are particularly productive of runoff. And so you can look at watersheds and you can think, well, should we, for the purposes of addressing water quality issues, treat every acre in a watershed as the same? And I think the answer is clearly no. You're going to have certain parts of watersheds that generate a lot more runoff. And what we find with these are they are ones that tend to have where their soils become saturated very quickly. So we are really, in our work, looking at how to target things within watersheds to places where they really have the biggest impact. So sort of a combination now of two things I'm trying to develop. One is thinking about the most cost-effective practices, and then the places in watersheds in which they have the biggest impact. And so when you think about a small watershed, this one being the Mont Hunt Tango, which is a small one feeding the Susquehanna River, we're looking at highly designed plans for it for experimental purposes. So that's within these watersheds. But even at larger scales, we know that certain parts of a large basin, in this case the Chesapeake Bay, will have different impacts on water quality. So this particular map shows how different parts of the Chesapeake Bay watershed, if you reduce nitrogen by a pound in some part of it, this is kind of telling you what the impact will be on bay water quality. So in the red part, if you reduce a pound of nitrogen, basically you're going to have a large impact. In the blue parts, if you reduce a pound of nitrogen, you're not going to have nearly as high an impact. So this is to suggest that when we're thinking about making the most out of our resources, we can think about targeting or at various scales and in various ways. So at the macro level, we have watersheds that are more productive of nutrients than are others. And as we narrow down on those watersheds, you're going to find areas within those watersheds that are much more productive of nutrients than are others. And then we've developed this idea that for cost-effective control, we want to target certain practices. And when you start doing this, you begin to recognize that there are possibilities for greatly reducing the cost of pollution control in agriculture. So sort of summarizing this, significant cost savings, and I'm going to show you some numbers on this, can be achieved by efficient BMP selection and spatial targeting in a watershed-based approach. So not anything anywhere, which is our current approach, not everything everywhere, which is sort of what the current watershed implementation plans for some of the Bay States call for, but really getting the right things in the right places. So this is a study the results of a study I did for the USDA Office of the Chief Economist on the cost of cleaning up, well, actually on the cost of the Chesapeake Bay TMDL for agriculture. So I have over there in the left column the states that have to comply. District of Columbia is also a government entity for the Chesapeake Bay program, but it doesn't have agricultural in it, so that's why I don't include it here. Then I have the annualized cost of a couple of different approaches. One is the annualized cost of the watershed implementation plans that the states developed to comply with the Chesapeake Bay TMDL. And what they did is they would specify various types of BMPs that they would install in certain amounts to achieve the goals. And so you'll see what the TMDL, as they have planned it, cost them. And then what I did in this study for the USDA is I looked at if you were to follow this approach of targeting areas and targeting practices for cost-effective control, how much money could you save? And I will say that in doing this, I used the Chesapeake Bay model for the sort of the water quality impacts part of this, and the Chesapeake Bay model is defined at a fairly gross scale for the purposes of watershed management. So small watersheds in which you want to target things in particular places are not represented in it. So these estimates will actually be not as great as they possibly could be in terms of cost savings. But what you'll see there on the right-hand side is that by targeting large watersheds and by targeting practices, you can save a lot of money in terms of reducing pollution control from agriculture. So Delaware, 80%, Maryland, 85%. And those are significant cost savings through the use of these methods that I'm talking about for targeting. So that's sort of from a planning standpoint how you might think about how utilization of our science of water quality protection and economics of water quality protection together can help us figure out better strategies than have been applied in the past and really under our conventional approach, which is the voluntary compliance approach. But the next thing we have to face is we can come up with plans, but we need to implement them. So we need to get things on the ground. And so what I have here is a table that describes to you various types of policy approaches that we can think about. So, so the rows on this table are about what you target when you when you want to manage pollution control practice adoption in agriculture. So the first one is practice-based, and so practice-based is kind of what we do now, and what you do in that case is you identify practices and you focus on the inputs to water quality protection. The next one is performance-based, and in this case what you do is instead of looking at the practices, you look at the outcomes. So you want to know what they do in terms of actual reductions. Now, knowing that agricultural pollution is non-point, you could say, well, how are you going to measure performance? And clearly that's a problem. But we do have a lot of work on models that help us at least understand how adoption of BMPs would influence runoff from farms and ultimately the delivery of pollutants to places like the Chesapeake Bay. So while we can't observe it, we can model it to varying degree. Of course, a lot of uncertainty in these models, but they're useful. And then finally, there would be strategies that I call mixed, and they would combine those two elements. So that's kind of what you think you would observe in compliance. The columns are the ways that you induce people to do things. And so there's carrots, and by carrots I mean payments or financial assistance that reduce the private costs of BMPs to farmers. So cost sharing is a common one. So we help farmers adopt practices by helping them pay for them. That's what NRCS's various programs do, like the Environmental Quality Incentives Program, which is EQIP. Tax preferences, we have tax preferences in Pennsylvania for BMP adoption. So those combine practice-based stuff, cost sharing for practices or tax preferences for practices with payments to farmers. Performance-based, water quality trading is an example of a performance-based policy. And the way that water quality trading programs have been designed in the Bay States and in most places is that point sources of pollution pay farmers to adopt BMPs to offset pollution reductions that point sources don't have. So it's a carrot for the farmer. Conservation performance auctions is another one. And in this case, you have reverse auctions in which farmers can sell pollution reductions to agencies or to others. There is an example of this in the Little Miami of Ohio rivershed, in which they use reverse auctions to purchase BMPs from farmers. Bottom one is conversion of highly erosive lands to vegetative covers based on a benefits index. So it focuses on a practice, but the practices are evaluated by the benefit index. Then there's sticks, cross-compliance, which is a program where if you get to participate in beneficial commodity programs in agriculture, you have to also undertake conservation programs. Input taxes, they use these to some degree in Europe. Pollution taxes, rather than, say, paying farmers to reduce a performance metric like nutrient credit, you might tax them. Product taxes, so something like fertilizer tax. And then on the far side, we have mandates. So this is for CAFOs, these large confined feeding operations. They have to comply with NPDES permits, which specify technology, stream setbacks, and various other ones. So what this table tells you is that we construct pollution policy instruments by combining some measure of performance, and it could be a practice, a performance, or some mixture, with some kind of thing that is intended to induce it, and that could be a carrot or a stick of various kinds, or just by telling people what you want them to do. So in thinking about what of those we'd like to have, clearly one thing we want to think about is their effectiveness, which ones of those work best in terms of producing the ecological benefits we would like to have. But then we also want to think about their costs, because we do have limited resources. And if you look at the states in the Chesapeake Bay watershed who were trying to address the Chesapeake Bay TMDL, you will find that all of them have problems. Well, I don't want to say all, but nearly all have problems related to resources, their own resources, to get done what needs to be done. So costs are going to be those that the farmer bears. So there are those costs. There's government costs, and these are very important for planning and administration, payments to farmers, planning costs, and what we call social costs. So social costs are basically the farmer's private costs plus government costs. And then if there's ancillary ecosystem service benefits like carbon sequestration, we'd want to subtract those off. I don't want to go too much into what costs are, but the costs matter a lot. And so the next thing I want to do is start to think about how you put these together in constructing programs. So this is a very simple diagram for suggesting that things are not equal. So on the bottom axis, we have the social cost of various practices, and on the vertical axis, we have the water quality benefit. And here I want to convey the idea that some practices are very high cost and not very effective. Some of them can be very low cost and very effective, and some of them might be high cost and low effectiveness. Well, anyway, so we have these variations, and I've kind of stuck things here where I believe they should go. So the ones that are sort of give you high water quality benefit but are also really expensive are extensive farming practice regulation. You could get a lot of water quality benefits out of it, but it would be, by virtually all economic research that's been done on it, very, very expensive way to go. The current method is over there at low cost and also low benefit. So voluntary BMP adoption doesn't cost, yeah, it's not costly, but it's not as costly as others, but it really doesn't get the job done. So in looking at things that get the job done and that have acceptable social costs, it's really up there in the northwest part of this diagram that we find the kinds of programs that would work well. So conservation auctions, water quality trading, and some well, I have there some farming practice mandates. I believe that in many cases, one of the things we should do is regulate certain kinds of practices in certain kinds of places because it's very cheap to do. So I think things like keeping cows out of streams is a real good idea, and we shouldn't use incentives to try to get it done. We should just do it. I think there's other things that would be in that domain as well, where just certain types of farming practices in certain places are just the right way to go, and we shouldn't worry about policies other than mandates to get them done. So we have these types of variations in social cost, but when the states, which are responsible for doing things, have to think about what needs to be done and how to get it done, they have to think about the cost to them, and the cost to the government and the overall social cost are not the same. So the government has to hire people to do work, has to get people out there to make plans and to monitor, enforce, and things of that nature. The private cost, their costs do not include the cost that the farmers incur for BMP adoption. So this is a sort of a different ranking of these various methods according to the government cost. And again, I have up in that northwest corner the ones that I think from a government cost standpoint and water quality impact make the biggest difference. So water quality trading, and again, some farming practice mandates, which really reduce costs quite a bit. Some of those things that were up in the northwest in the previous diagram have moved into other places in this diagram. So social cost and government cost don't necessarily always line up together. My northwest quadrant there does have those that I think do. So when I'm doing that analysis, I'm really thinking about what you're doing within a large watershed like the Chesapeake Bay and the smaller watersheds located within it. The next thing I want to talk about very briefly are what I think of as landscape scale problems that we need to be addressing also, but really can't be addressed specifically or best through actions within watersheds. So this is a diagram of the flow of nutrients across the landscape from the Midwest into the Chesapeake Bay watershed. So we in the Chesapeake Bay watershed have a very animal-intensive agriculture. We grow some of the feed for these animals in the watershed, but we import a lot of the feed from the Midwest. So over in the Midwest, over on the left side of this diagram, we're taking fertilizer, we're putting it on the ground, we're growing crops, we're moving those nutrients from the fertilizer in the soil then into the crops. Then we send it to the feed mill, and we ship it off to the Chesapeake Bay watershed. And in the Chesapeake Bay watershed, animals are very important, but the animals only use up a fraction of the nutrients that we feed them, and the remainder goes into manure and then goes onto the ground and then results in the externalities that we have. So about a quarter of our nutrients are going into the animal products. The other is becoming environmentally available. So we're shipping nutrients off from the Midwest and moving them into a very nutrient-sensitive environment to feed our animals. And so this really suggests kind of a landscape scale problem that we have. I would suggest that in thinking about how we reduce stresses in a place like the Chesapeake Bay or elsewhere where they have similar types of things, you really have to think about how the agricultural system is influencing the pressures in watersheds. This is sort of a diagram of the same thing, and it kind of highlights again that we have a nutrient surplus region in the Midwest, and we're shipping it off, to our nutrient-insensitive environment and resulting in significant nutrient surpluses in the Chesapeake Bay watershed. And that's not the only place where the Chesapeake Bay watershed is getting nutrients. We also get it from atmospheric deposition. Some of this comes from denitrification and from ammonia emissions, but a lot of it's coming from burning fossil fuels. So the Chesapeake Bay watershed is getting nutrients, nitrates, from a larger airshed that includes other parts of the country. So again, the idea is that we are getting, we have landscape scale processes that we really have to think about in thinking about how to reduce these nutrient problems. So I have one more minute for I think the time that I was allotted. So thinking about what this means overall. Again, I want to emphasize that we can address these nutrient problems from ag cost effectively through using planning of the types that I suggested that emphasize putting the right practices in the right places, really focusing on cost effectiveness of practices, and looking at the best places within watersheds to put them. The next thing we need to do is think about what policies do that, and I have suggested some types there that I think perform well, both from the standpoint of the cost of the government and the social cost, and resources are limiting, so I think those are very important considerations. And then, but in addition to those kinds of watershed scale measures, we need to look at the landscape types of drivers that are problematic. And I have down there as sort of my bottom message is that we need to get the prices right. So one of the reasons why we have this landscape scale problem is that we don't have the cost of the externalities of agricultural production in places like the Chesapeake Bay being reflected in the costs of the products that are being produced. And if we would internalize that cost, and some of the mechanisms I have been talking about would do that, then it would certainly help shift production systems so that they're less nutrient intensive, and it would also help shift production systems from nutrient-rich environments into different environments. And so that's one thing that getting prices right would do. Another thing about getting prices right, though, is things like carbon taxes or other energy measures where our systems have the characteristics they do because we don't charge all of the social costs to them. So as an example, in the Midwest, we produce a lot of ethanol because of subsidies for ethanol production that Congress has done, and we justify those largely for the purposes of reducing carbon emissions, and there's debate about how much they do. But one thing we do know about ethanol production is that it is, well, it's corn intensive, and corn in the Midwest is a significant cause of water pollution. And so what we have done with ethanol subsidies is rather than getting the prices right, we've actually priced things to encourage water pollution. So to reduce the systemic pressures on water resources, we really need to think about getting the prices of things right on multiple fronts. So that is the end of my presentation, and I'm very happy to answer questions.
Thanks very much. It looks like there are some people typing questions. While they are doing that, one of the things I wanted to ask you was, how do you think the implementation of the different things you mentioned at the very end could actually happen? And one of the things I'm thinking of there is the initiatives in France where they've been trying to pass this on to the consumer of water, and they end up having to pay an environmental restoration fee in addition to the water treatment and wastewater disposal fees. It's kind of hard to see how many of these things, other than a regulatory pressure, would get addressed. And I'm sure you have some ideas on how this could happen.
So in getting them to happen will be very difficult, and my hopes are not high on the whole. And the reason, I think when people see that there are risks to their own health from a water quality problem, they're very eager to have it addressed. But because the risks from nutrient problems are more to ecosystems, I think people really don't understand that there are consequences for them. They're more diffuse and they're less personal. And you can show that ecosystems have tremendous value from the ecosystem services they produce, but they just are not as compelling to people as health risks. So if you have a regular citizen looking at a stream that is bubbling along through a golf course, they might say, "Oh, that stream looks really nice," and they don't understand that it's probably ecologically dead. And so just the way that people perceive water quality is very different from the way that an aquatic biologist would characterize water quality. So I think that's a big problem. So these things are expensive, and getting people to pay attention to them is, I think, a real challenge. So I think what we have in the Chesapeake Bay is a unique setting that creates regulatory pressures to get things done. And we may see that in the Ohio River Basin, although they just got a reprieve on when they have to do things there to clean up the dead zone issue. So I guess it's not easy, and I don't have a solution for it.
So I'll come back to this, but there are three questions there. Maybe easiest if are you able to see the questions?
I can. Um,
Okay.
so to James Rising's question, I'd love to get the prices right. And certainly economists are always talking about getting the prices right. Um, and I think possibly as we continue to wrestle with things like climate change, which we desperately need to have a carbon tax to address, um, hopefully the idea that certain things can be gotten done much simpler by pricing them than by really complex regulations, it might help do it. But I think it'll take a while. Let's see. To Eliza's question, I do think we see a lot of innovation by companies that are trying to do things with nutrient recycling and recovery. The big problem they have is that there's really no business model that will pay them for it right now. So until we have sort of the regulatory environment in which they can be paid, I don't think companies will be able to do much. And this is something that I see here in Pennsylvania. We have a number of entrepreneurs who have figured out very good ways to address nutrients, but they cost, and they can't get the resources they need to do it. Let's see, Tony's question, the difference between, I'm not sure I can understand what that one is. And on the dead zone, I was at a conference in September in which it was not intended, but it happened anyway, sort of a comparison of policies for the Ohio River Basin and the Chesapeake Bay. In the Chesapeake Bay, the pressures are strong, and I think we're moving at a fair pace. What I see in the Ohio River Basin is that the challenges are leading, instead of to more rapid approaches, really to sort of delay, and so I don't know what's going to happen. And okay, examples of successful water quality trading, there are, and I would highlight one on the South Nation River in Ontario, Canada, which has been very effective in reducing phosphorus problems resulting from ag and from point sources. Significant cost savings, and it's working. There is a nutrient trading program on the Connecticut River, which is working. Virginia has a new point source trading program. I don't know that much about it, but it looks to be working. So I think when you see water quality trading programs that are what I would call well designed, they've really thought about how to make drivers in the market to make it happen and to facilitate trading. I think trading programs have done a good job. There's a lot of them, though, that have been sort of jerry-rigged, and they don't do very much. So to Mr. Coleman's question, I think the no-till is something that I think I'm not completely up to speed on the issues with no-till. Clearly, no-till is very good for reducing runoff, but when you're increasing runoff, we also increase infiltration, and so there can be some trade-offs between pathways of nutrients to water because of no-till. But I think generally we think of no-till as a really good practice versus plow arable farming, and I'm just assuming you mean sort of conventional tillage systems. So for so one of the problems we have with with the point non-point trading with Upmanu's last question there is this issue of uncertainty, and uncertainty is often cast as a reason not to trade with non-point sources. But I would suggest that it's actually a good reason to trade with non-point sources because a significant part of our variability in nutrient loads comes from non-point source pollution. And so we know especially that large runoff events will wash a lot of stuff off of agricultural landscapes into the water. So to reduce the variability of that means I think we really have to change agricultural landscapes so that they are less problematic. And so we might not be able to prescribe with or describe with great specificity the effectiveness of practices, but we do know that if we get no-till, riparian buffers, and various measures like that that can reduce no-till, then we're really going to be reducing the risk of water quality damaging events compared to existing landscapes. So trading programs are often designed to discourage or limit point non-point trading because of the idea that the point sources give you better certainty. But when you do that, you also limit the gains from reducing non-point risk. So I've been called a heretic for this, but I believe that jiggering trading programs to actually get a lot of non-point reductions to offset point source reductions is a really good idea for reducing variability. I've been called a heretic for other reasons too.
Okay, thanks very much, James. I don't know if there are any others typing at the moment. Doesn't look like it. So maybe I'll take the last few minutes here and ask you follow up on the last thing. What I was specifically thinking of was many times the EPA has put in as part of the TMDL process BMPs which require farmers to collect animal waste and store it in lined ponds. Unfortunately,
Right.
the minute you get an extreme precipitation event, you get a major loading into water bodies, and then you have a chronic effect of that particular loading. So it seems that there has to be some thinking as to how to address extreme events on both sides, in addition to business as usual, so to speak. And I haven't really seen that much discussion of it, but then I don't work in this area, and that's what I was trying to ask.
Yeah, you have identified, I think, the particular practice that is sort of the counterexample to what I said. So what you do is, in that case, well, again, a lot of our non-point pollutants move off in high runoff events, and then what we do with those is we kind of store up all of the waste, and then we have the runoff event, and we dump it all in all at once, which causes an intense problem. Hopefully, we design these things better so that doesn't happen. But setting aside that particular case, I think this is actually an interesting scientific design issue. We do know that there is uncertainty about the effectiveness of practices. We do know that there's a lot of uncertainty in our water quality models. But we don't really formally build these uncertainties into the policies that we address. So if you look, for example, at many TMDLs, they're evaluated looking at the annual average impact of long-term annual average impact of a practice on water quality. So all of the variation about that is ignored, and also lags are ignored. So you might sort of evaluate things completely differently if you evaluated BMPs for extreme events and evaluated them for sort of the time path of the pollution reductions that they produce. because we know that many of them are treated for policy purposes as though they will have an instantaneous impact when they're installed, but they may not actually have an impact for 5 or 10 or 15 years or even more in some cases.
It looks like, thanks. I think this was very interesting. Um, I always end up with more questions in a way when I hear um, these talks on processes that are inherently complex because the things you talked about touch on both human behavior in terms of the success of the implementation of these ideas, whether it's on the trading realm or the physical side, as much as they do on things that would make them work. Um, I guess my last question for you is going back to my first question in a way. Do you see processes where, short of regulation, there's a way to intrinsically incentivize proper actions for people, recognizing that their impacts are external and not internal, and hence they don't let themselves see their own health being threatened?
I honestly, I think we can talk about various methods, and we've talked about them for a long time, but they don't happen, and they can happen in different ways. So, I think when you look at the ag problem, you could say, well, it would be very, very beneficial if we could develop cooperatives that would utilize green production methods, and then they could brand their food in ways that would indicate that it was produced sustainably. And you do have companies, and this I guess goes back to a question that was asked earlier, that are very interested in sustainability in the products they purchase. And I think you see various large grocery stores and other types of things that do that. But I'm not convinced that that sort of voluntary method will work because it's really difficult to coordinate. And I think when it comes down to it, people may not be willing to pay a price premium if there's a cheaper product there. And so I think that regulation is essential for progress.
Thanks very much. Looks like no one else has a question. This was really insightful and I appreciate it, and I look forward to maybe following up offline and getting your ideas on some of these things. Really
Okay, well, thank
appreciate
you
your
very much.
taking the time to do the call.
Well, thank you very much for having me. I enjoyed it very much, and I would look forward to an offline conversation.
Great, thanks.
Thank you. Okay. Thanks, everyone. Thank you. Bye.